So it's a pleasure to introduce the last speaker, not just of today, but the whole conference, George Boxer, also from the École Normale Supérieure de Lyon. And his title is Higher Coleman Theory, Part 2. Please, George.
Okay, thank you very much for the introduction and the invitation to speak at this conference. I'm just going to warn you that this is my first Zoom talk, and I'm also very new to my setup here, so I hope it won't be a complete disaster. But with that out of the way, so the goal is to, well, explain a little bit more about these overconvergent cohomologies that Vincent has discussed, and in particular explain a little bit about how the support conditions are working. So I remind you of the general setup, but so we have GX, a Shimura datum of abelian type, and this gives us our tower of Shimura varieties for levels K. And we're going to assume that P is a prime such that GQP is quasi-split. I mean, this is somehow the natural condition that there will be sort of enough sort of UP operators to get a good theory of p-adic modular forms. Okay, and so as in Vincent's talk, we have a choice of a torus, a Borel sitting inside this parabolic P mu, which has a levy M mu. Okay, maybe I should say that F over QP is a finite extension splitting G. And so in general, of course, B can be defined over QP, but P mu and M mu are sort of only going to be defined over maybe this field F. Okay, and so we have this vector bundle dictionary. So for sorry, what am I writing? For mu dominant weight, we can associate an automorphic vector bundle VK over our tower of Shimura varieties, and so then we have the flag variety and this group of constant representatives. So the flag variety is the flag variety P mu mod G. Again, we think of this as living over this field F. And we have this set of constant representatives. Okay. And now we also have the Hodge-Tate period map. So we're going to, in general, view our level as factoring as K upper P times K lower P. And in fact, I will, as Vincent did, just assume that KP is the Iwahori for simplicity, although we can work with any group with the Iwahori factorization. And then we have the perfectoid Shimura variety of level K upper P with its Hodge-Tate period map to the flag variety. And we consider this picture as in Vincent's talk. So we consider the flag variety mod KP just as a topological space, and the Shimura variety at finite level maps to it. And somehow what we're going to be doing in this business is that, well, on the flag variety, we have the action of the group GQP, and that's very simple to understand. Now, this quotient is maybe a little bit scary, but we still have sort of actions by the sort of Hecke operators of level KP. And somehow, in some sense, it's sort of not too bad to understand the Hecke action on this quotient, because it's basically like understanding the action of this group and then sort of averaging by the Iwahori. And of course, we also have the Hecke action on the Shimura variety, which, well, seems more complicated, but we can use the Hodge-Tate period map to sort of keep track of it. And we'll try to use in particular try to use it to choose the support conditions that will work for us, as I'll try to explain in a moment. So I really want to draw some pictures in this talk, draw some pictures of support conditions and the action of the Heck operator. And in order to do that, I want to draw the pictures in an example. So we have this example for illustrative purposes, but somehow the arguments that I explain are actually not really going to use the pictures. So it's just so I can draw them. And that's this group which Vincent mentioned. So maybe we should fix f over q, a quadratic extension. And let's assume that p is inert. Sort of always going to be the more interesting case than p splitting, at least. And we're going to look at the group G equals the restriction of f over q of GL2. So this is the sort of case of a Hilbert modular surface. And this has already been used as an example many times in this talk. And in particular, has a nice feature that it's a surface, and I can sort of feel like I'm drawing pictures of surfaces. So, so in this case, P mu is conveniently just B. This group of constant representatives is conveniently just the whole Weil group as a result, because the Levy is a torus. And as Vincent said, it can be viewed as just two copies of, well, 1 in W, where W is the non-trivial element of the Weil group of GL2. And so, okay, so just, let me just draw this diagram again. So, okay, so I want to draw a picture of the flag variety, and that's pretty easy because the flag variety is just, well, getting the rational structure right. It's the Weil restriction from QP squared to QP of P1. And so geometrically, it's just a product of two P1s. And so I'm just going to always draw it as a square. And we have these 4 points, which correspond to the elements of the Weil group, which are infinity, infinity, 0, infinity, infinity, 0, and 0, 0. And so these 4 points are exactly the sort of torus fixed points in this P1 times P1. And there's going to be essentially one Heck operator in this case. And so that Heck operator is what you might call the UP operator, but I'm going to call it T because U is going to be an open set later on. So T is going to be this Heck operator, which is associated to the matrix P inverse 1. Okay. This is really not very good, but you can read it, I guess. Okay. And so, well, how does this correspondence act? So, okay, so whenever I draw these pictures, I'm always going to be drawing a picture of this space because that's what I can draw a picture of. But I might really be thinking that I'm drawing a picture of this space or even this space. And so the rule is always that we should only draw things which are kind of Iwahori invariant up here, and then imagine that we're pulling them back to here. Okay. So, so at least if you look up here, the dynamics of multiplying by this matrix is completely simple. Basically, what it wants to do is take you sort of towards this point. So, so this point is somehow an attracting fixed point for the action of this Hecker correspondence UP. This point, this fixed point up here is sort of a repelling point. And these, what's more interesting is that these two fixed points at the sides are kind of having both the attracting and repelling behavior. So coming from this, sorry, you can't see that. Coming from this direction, you're getting attracted, and coming from out of this direction, you're getting repelled. Okay. And so, of course, the usual theory of overconvergent modular forms lives at this point, infinity, infinity, the sort of attracting fixed point. And I'm going to recall in a sec how you use that fact that it's the attracting fixed point. But let me just remind you something that Vincent has also said. So the fibers of these 4 points, they correspond to Igusa varieties, or rather the sort of image of Igusa varieties in the Schmor variety at finite level. So these two are ordinary. So infinity, this point corresponds to the case that the p-divisible group of your Hilbert-Blumenthal abelian surface is ordinary, and you've chosen the canonical subgroup, the multiplicative subgroup, and over here, the anti-canonical locus is where you choose the étale subgroup. You're ordinary and you choose the étale subgroup. And then these 2 points, as Vincent has mentioned, correspond to, well, they're not ordinary. They correspond to the p-divisible group Lubin-Tate 1 times Lubin-Tate 2, which is a supersingular p-divisible group. So maybe I should say that, because it's, well, something that might be helpful to say is that, I mean, of course, on this flag variety, we have this Newton stratification, and in this case, you can actually describe it. So, so maybe I should recall that. So the QP points of the flag variety are sort of, well, they're P1 of F, P1 of QP squared, but in the coordinates that I'm writing things, they're the points which are sort of X and X bar for X and P1 of F. And here, this bar is just Frobenius or conjugation. Sorry, this F. Okay. This F is supposed to be a QP squared. And so in particular, what you see is that these 2 points are actually not rational points. They're not in this set because, of course, the conjugate of infinity is infinity, not 0. Okay? So you see that they're in the supersingular locus, and in fact, they correspond under this sort of Schulze-Weinstein correspondence to this p-divisible group Lubin-Tate 1 times Lubin-Tate 2. Maybe I should say what that is. The point is that geometrically, there's kind of only one Lubin-Tate group, except that you have to fix the CM type. So in other words, these are p-divisible groups over OC, and they have an action of ZP squared, and you have to choose which embedding ZP squared acts on the Lie algebra. So there's 2 choices, and you take 1 copy of each of them. And then, of course, the choice of the 2 points correspond to choosing sort of either the subgroup, so your Iwahori level to be either Lubin-Tate 1p or Lubin-Tate 2p. And so, in fact, I mean, not thinking about this picture from the point of view of the flag variety, but just thinking about it from the point of view of p-divisible groups, you can see that these p-divisible groups with Iwahori level structure are something like fixed points for the UP correspondence. Because in fact, like if you take Lubin-Tate 1 times Lubin-Tate 2 with, say, the level structure given by Lubin-Tate 1p, then you can take the isogeny, which is multiplication by p on Lubin-Tate 2, and that gives you a sort of point of the correspondence going from this point to itself. I'm not sure how much sense that makes, but somehow the point, I mean, very roughly, like the idea of why we're considering these fixed points in the first place is that we're trying to study the part of cohomology where this Heck operator acts invertibly, and sort of morally, you could kind of expect that this is going to be concentrated near all the fixed points. It's just that you kind of have to understand in some higher cohomological terms what's happening near the kind of non-attracting fixed points. Okay. All right. So now I want to talk about how to choose support conditions and how to prove some kind of analytic continuation result that says that the support conditions don't really matter. So I want to recall how this works in the classical case of overconvergent modular forms. So let's talk about analytic continuation in the classical case. So, I mean, here drawing my picture again. The classical theory is living near this attracting fixed point. And what we do is we take some open set, which I'll draw with a dotted line because there will be closed sets later. So maybe I'll call this open U. And because of the contracting behavior, at least unless we choose this set U very stupidly, T of U is going to be a subset of U. And in fact, it will even be strict in the sense that the closure of T of U is contained in U. And so how does this analytic continuation argument go? Well, the idea is we want to consider some space of overconvergent modular forms. So overconvergent modular forms, actually, let me do this a little better. Let me start with sort of sections. So overconvergent modular forms, which live on the set T of U. And now the point is that, well, we want to apply the Heck operator T, but we can do better than just landing in the same space. Because after all, if we start with any point in U, somehow the correspondence sends all the points sent that you get sent to by the correspondence actually land in T of U. And so that means that in fact, you can define T of a modular form of T of U, not just on T of U, but on U. Okay? Because after all, what is T? It basically means you look at all the points that this point gets sent to by the correspondence, look at the values of the modular forms there, do something to them and sum them up. So it makes sense on U. And now, of course, we have the restriction map. Back to T of U. And okay, so now a bunch of very nice things happen. So the first nice thing is that this map is going to be compact. So I should say, of course, all these spaces are going to be huge because, I mean, we're taking just sections on some, maybe you could imagine if I choose these right, they could be maybe aphanoid or something, but these are going to be huge things like big infinite dimensional p-adic topological vector spaces. But the restriction map for sections on a strict neighborhood will be a compact map for the topology on these spaces. And so that means that the sort of whole Heck operator T, so I just warn you, I'm going to label millions of maps T, and we'll just have to deal with it. So this T, which is the sort of endomorphism, the UP endomorphism of this space of overconvergent modular forms, is thus also compact. And so we have a spectral theory. But also, we learn from this that the finite slope parts of these two spaces are the same. Okay, and I can even maybe spell out in gory detail why that's true. I mean, maybe it's obvious to you, and certainly if you study the subject, it's obvious to you, but the way, I mean, I always like to draw this diagram. So the point is that, well, let me not write the sheaf for the moment because I'm running out of space. Sorry. So we have sections on U, we have the Heck operator, and we have the restriction. Heck operator. And the point is that in this diagram, we have this map up here, which is actually giving us a factorization like this. Unfortunately, I also called it T. And now you remind yourself, well, what does it mean for this to be an isomorphism on finite slope vectors? Well, it means that it's an isomorphism on sort of generalized eigenvectors with non-zero eigenvalue. And you can easily use this diagram to check that. Maybe we do it on just eigenvectors. So like, for example, if you have an eigenvector with a non-zero eigenvalue here, its restriction can't be zero because down here, you would get something non-zero because you're getting just the eigenvalue times the vector. And similarly, if you had an eigenvector here, you see something which it's the image of, namely you go here and then you divide by the eigenvalue and you'll get something that maps to it here. And so you check that that also works on generalized eigenvectors. Okay. So this is the classical analytic continuation argument for overconvergent modular forms, and I apologize to the specialists if I'm boring you, but what I want to do now is describe a version of this for cohomology with some kind of support conditions, which which will work with higher cohomology. And in fact, the first thing I should say is, so if you were to, so maybe we're going to from now on be looking at one of these points. If you tried to do the same thing there, it wouldn't work, because after all, if you took some open neighborhood of this point, maybe like that, what happens when you apply the Heck operator to it? Well, you're going to get some other region like this. It kind of gets squashed in this direction, but it gets expanded in this direction. So you see that you can't even define, so if I call this maybe U, we can't even define an action of T on H naught of U in any natural way. So we really kind of can't get a theory of kind of overconvergent modular forms in the neighborhood of this point by just taking cohomology or just taking sections. And we certainly wouldn't be able to prove it's compact or prove an analytic continuation result because there's no operator in the first place. Okay. And now there is one objection that you could have to this, which is that, well, maybe you're just using the wrong Heck operator. So like, for example, at this point, there is something you could do to remedy the situation. We could, instead of using UP, we could use UP transpose, which has kind of the opposite behavior of UP. And sort of UP transpose will be sort of contracting at this anti-canonical locus. But, well, you can do that and get some theory, but of course, that's actually the same theory that you already have, because there's the Atkin-Lehner involution, which is kind of exchanging these 2 points and exchanging UP with its transpose. So that's really not what we want to do either. But somehow for these points, we can't even work with a different Heck operator. There's simply, so this is kind of one reason why I wanted to work with this example, because this is something that happens, I mean, for split groups, you can always take some combination of Heck operators, which kind of contract to any of these W's, but for non-split groups, there's really no choice of Heck operator, which will be contracting near this point. So we have to do something else. And of course, Vincent has already introduced this, which is to put some cohomology with supports. So oops. So instead, we take cohomology with support. And I can even draw in the picture the kind of support condition that you're going to want to take near this point and explain why it works. And I hope this will suddenly seem very simple and natural once I explain this. So the idea is, well, I'm going to draw an open set and I'm going to draw a closed set. So maybe I draw this open set U. So U is this open set, and then this closed set, so the stuff up here, and I'll call this Z. And we're going to consider R gamma of U intersects Z U of the sheaf V kappa. And so in fact, as I'll maybe explain in a moment, this is exactly the kind of cohomology with support that you're going to see when you consider this Grothendieck-Cousin complex and you just filter, well, anyways, I'll come back to that in a moment. So let's explain how to get an analytic continuation result for this kind of cohomology with support. So to do this, let me first just say something about this, which is that you should really think that this cohomology is just living on this intersection, on this locally closed set U intersects Z. And in fact, the point is that, well, first of all, it definitely doesn't depend on Z in any way other than the only place Z shows up is in this intersection. So we could replace Z with any other closed set which has the same intersection with U. But actually the same thing is true for U. We could replace U with any other open set which has the same intersection with Z. And the reason is that this local cohomology satisfies some kind of what topologists call excision, which allows you to change the U sort of away from the support. So really, we could just think of this as only depending on this locally closed set U intersects Z. But the reason I'm choosing U and Z, you'll see in a sec. Okay, so now let's talk about some functorialities. So the first thing that you can do is you can restrict the open set U. So if we have U inside a bigger open, we get a restriction map, which goes from the sort of big open to the small open. And there's something similar we can do with the closed. So if we have a small closed and a big closed, well, I mean, what is this functor actually? It's the derived functor of cohomology with support. And so if you have a section supported on the small z, you of course have a section supported on the big Z. And so you get a map which goes from this one to the bigger Z. Okay. Now, what we really want to do here is study how correspondences act. So in our picture, we have this Hecke correspondence C. So this is the sort of geometric correspondence which underlies the UP operator, or the Hecke operator I'm calling T. And so correspondences go left to right for me. So in other words, applying T to a point X, you take P1, you take P2 of P1 inverse of that point. But of course, since we're about to define an action on cohomology, the action on cohomology is sort of supposed to go the other way. So you're supposed to sort of pull back by P2 and then take a trace by P1 when you take the action on cohomology. Okay. So my claim, oops, what just happened? Something terrible has happened. Okay, I think I accidentally just went to Zoom, but everything is working still? Someone tell me if it's not working. Okay, great. Sorry about that.
No, it's good. Yeah.
I think I touched the thing at the bottom of my iPad. I'll try not to do that again. Okay. So, okay. So, right. So we're we want to, so the claim, and I apologize as I'm about to explain this claim in some really gory detail. So the claim is we get a map. This is the thing that you would discover if you just sat down and asked, how do correspondences act on cohomology with support? You get a map which goes from the thing with T of U intersects Z to the cohomology where you take U, but now T transpose of Z. Okay. And sorry, there's something else. So to get an actual action on the cohomology, we have over C a map of sheaves. P2 upper star V kappa to P1 upper star V kappa. And somehow this map of sheaves is just coming back. This is just coming from pulling back differentials. So somehow this correspondence is parametrizing some isogenies of abelian varieties, and we get a map like this, which we'll use to define the Hecke action on cohomology. Okay, so how do we define this map? So I'm going to start drawing it. And again, I apologize for explaining this in gory detail, but I think it's a little bit important. So I'm going to do it. So the first thing that we do, as I said, the first step in defining the action of cohomology is to take a pullback by P2. So now we're going to be living on the correspondence, C. So we have P2 inverse TU intersect, sorry, P2 inverse Z. Again, P2 inverse TU P2 upper star V kappa. Okay. And now, well, what is P2 inverse TU? So P2 inverse TU is P2 inverse P2 P1 inverse U. Okay. And of course, that is a bigger set than P1 inverse U. So now I have this restriction map where we use one of our functorialities above. And now we apply this map at the level of the sheaf. So maybe I also call this map T. So everything is called T to get to same support conditions. And now we kind of do the same thing by increasing the support to get to P1 inverse U, and I'll just write it and you can check that this is right. Sorry, P1 inverse T transpose Z. And now we take a sort of trace map. So see, now we have P1 inverses everywhere, and so we take the trace under P1. Okay, so this is the natural map, and this is the thing you would have discovered if you just sat down and played around. The thing I want to say, so there's one thing I want to say, which is, you see, I mean, for these three maps, we could have actually taken them in any order that we wanted. They sort of all commute with each other, but there is a good reason to take them in this order, which is that we wanted to be applying this map when the support is as small as possible. Somehow, I mean, the locally closed set here and here is bigger than it is down here. So let me just remark that, is that this only depends on T near this set. Which is something that, well, I was planning to use later, but I spent so much time on this that I probably won't. Anyways, okay, so now what do we do with this? So let's go back to our picture. So here's our point. Here's our set U. Here's our closed set Z. And well, we added these two other sets to the picture. So let's assume, as is the case in the picture, but in the sort of general setting, we now assume it, that T of U is contained in U and T transpose of Z is contained in Z, which is true in the picture, but sort of should also be true in the general situation that we take. So here we have T of U, here we have T transpose of Z. And note that now something kind of nice has happened, which is that we're at least seeing this kind of genuinely smaller neighborhood, T of U intersect T transpose of Z, okay? Which is maybe the kind of thing that we would want to see. So now what do we do? Well, let's take this map that we have and draw a little diagram. And okay, now let's draw the two spaces that we actually care about, namely this original cohomology with support, with our original support condition, and maybe this one with this smaller support condition. Okay, and now we have some functorialities. So here we can restrict, here we can extend the support, and sort of parallelly here we can restrict, and here we can extend the support, okay? So we have this little diamond, and the thing I like to say about this diamond is that you see that the two spaces that maybe we're most interested in comparing, there's no map between them. At least there isn't until you draw this T in the middle. There's sort of, they both get a map from this space and they both map to this space. But now, once you have this T, so using T, you define endomorphisms of all four spaces, which I also call T. So how does this work? You just go around the diagram. So like for here, you go around like this. For here, you go around like, sorry, you go around like this or around the top. So I should say that these two compositions are the same. And similarly for the others. And they all have the same finite slope part by the sort of argument from before. Sorry. Okay, so this is this sort of basic analytic continuation result for cohomology with support. And of course, now you can keep going. So, so if you are in the situation that furthermore, sort of U contains TU, which contains T squared U, and so on. And similarly, Z contains T transpose of Z, which contains T transpose squared of Z, and so on. Then what we can do is we can just keep extending this diagram. So maybe to make it short, I'll write R gamma NM to be R gamma of T to the N of U intersect T transpose to the N of Z of T to the N of U of V kappa. And so now we get this diagram with sort of R gamma 0, 0, R gamma 1, 0, R gamma 0, 1, 2, 0, 1, 1, 0, 2, and sort of all these maps like this, and sort of all of the R gamma NM finite slope are isomorphic. And so this is this thing that Vincent has introduced, this sort of R gamma W, depending on only the Weil group element, BK. Okay, so the point, all right, so something I'll just say, so is that in fact you can go a little bit further and consider support conditions which are not showing up by just iterating the Heck operator on your original support condition. And what you even see is that any sort of sensible support condition which kind of fits between this sort of double sequence of support conditions will also work. And just to go back to the picture, I mean, really the important thing is that you're choosing this kind of locally closed support condition so that the sort of open wall is kind of getting contracted and the kind of closed wall is getting expanded. So anyways, okay, so I hope that explains something. And now, okay, so what was the so what's the recap? We start by computing the cohomology of the Schmor variety. Using a filtration, and somehow, but so what does that filtration look like in our picture? Well, it's kind of, let me actually just draw it. So I draw it as a decreasing filtration. So we start with Z0 as the whole space. So Z1, Z2, and I guess Z3 is going to be the empty set. So I drew too many pictures. So the filtration just looks like this. We start with this closed set, and then somehow this closed set. Okay, so that's a picture of a filtration. And so what are the terms which show up in the E1 page of this spectral sequence? So so we get 4 cohomology groups. Well, 3, but so actually I even draw the pictures because I'm enjoying myself here. So so here the first term is going to be exactly this open, so it's Z0 minus Z1, and that's sort of usual overconvergent modular forms, but with a kind of huge radius. Then the next term looks like this, so exactly the kind of support conditions I was drawing before. And of course, the last term looks like this. And then I should say that you can show that, well, at least if you choose this picture correctly, this breaks up as the kind of direct sum of the 2 cohomology groups, like this. Okay, and so the thing to say is that at this point, we really didn't do anything yet because, of course, you can take any topological space, you can filter it however you want and get a spectral sequence like this. But the reason we do it like this is that we now have this analytic continuation result that I've just explained, which relates each of these cohomology groups to something which is now very close to the fixed point, as close as you want. In fact, at least after passing to the finite slope part. So for example, you can take the blue support conditions. Okay, and this is already a huge victory because, I mean, we started with these three cohomology groups, which are somehow covering the whole Chamorro variety. And now we have these four cohomology groups, which are only seeing a tiny part of the Chamorro variety. And so it feels like we've just gotten rid of most of our Chamorro variety, and that's obviously a good thing. Okay, now what are we actually going to do with it? So I've managed to spend most of my talk on that, which I think is kind of okay. So what do we do now? So, oops. So we use the fact that R gamma W B kappa can be computed on an arbitrarily small neighborhood of the Segusa variety. So of pi Hudge Tate inverse of PWWKP. Show, well, the first thing is a slope bound on sort of the UP operators acting on R gamma W B kappa. And so, and this has as a consequence Coleman classicality. So, I mean, this is basically exactly what Vincent was explaining in his talk, except, well, not actually explaining how to do it. And I guess I'm also not going to explain how to do it. But the point is that you get, you look at how, you look at the integral properties of the UP operators sort of on the Segusa variety. And what you see is that there's kind of incompatible lower bounds for the different terms as the weight kappa varies. And so what that allows you to do is it allows you to basically choose a sort of small slope condition to kill all but one of the W's. And then you get a Coleman, you get sort of Coleman classicality. And at least that will work as long as your weight is kind of regular. So this is basically what Vincent has explained. So the next thing is vanishing theorems. And so here we use the affineness of pi Hudge Tate, as Vincent has said. And I guess I can just tell you maybe the basic vanishing theorem, which you prove, is that R gamma W V kappa minus D. So if you take the cuspidal sheaf, is concentrated in degree 0 up through, sorry, the length of W. Okay. And the third thing is you use this to periodically interpolate. Okay, so now I'm maybe supposed to say something about that and about eigenvarieties to finish the talk. So in fact, I mean, this business of periodically interpolating, it's very similar in a sense to what was already done. Sorry. So it's very similar to what was already done in this work of Andreade, Iovita, and Poloni, and the previous works and subsequent works on this kind of thing. So the idea is that you have these sheaves V kappa corresponding to algebraic weights, and they don't really vary periodically, but maybe they sit inside some much bigger sheaves which do vary periodically. So since I have basically 0 time, I'm going to say basically 0 about this. So doing the same thing that AIP do, So one defines big sheaves for every W in MW, and now not a algebraic character, but a continuous character. Let's say CP cross. So I'll call this big sheaf V mu, V nu n, because it's sort of modeled on a locally analytic induction. So it's a huge sort of infinite dimensional thing. And these live on small neighborhoods of this pi Hodge-Tate inverse PW times W times KP. Okay. And well, you can, and what I should also say is for an algebraic weight, there is some relation, and there's something slightly confusing about this relation. We get a map V kappa sitting inside, well, you'd want to write kappa, but we actually put W inverse dot kappa here. And I'm not really going to explain exactly why that is, but I'll try to say something in like the last few minutes I have. And then there's locally analytic BGG resolution. And what that allows you to show is that somehow that under a different small slope condition, which we call mu small slope, or maybe strictly small slope, but doesn't really matter, this induces an isomorphism. So this is another classicality theorem. And it's very similar to what Andreatta, Iovita, and Poloni do. Again, we need this small slope condition. Okay. And so when you combine this with the previous sort of geometric classicality theorem, you get a classicality theorem linking the cohomology of these big analytic sheaves to the classical cohomology of the Schmor variety. And I should say that when you combine these two small slope conditions, you do get essentially the usual small slope condition in the sort of classical theory, I mean, well, in the, for example, the theory of zero-dimensional Schmor varieties, which has a sort of Galois theoretic interpretation. Okay, so now these things we can also construct in families. So we can construct an eigenvariety just by drawing it into the usual machine. And maybe I just state a sort of theorem about the eigenvariety and then finish my talk. So there exists an eigenvariety mapping to weight space. And I guess weight space is, we take the Iwasawa algebra of TZP, and we take its generic fiber. Okay, and so there's kind of only one eigenvariety, and there should only be kind of one eigenvariety, but then on that eigenvariety, you have maybe many different theories of Coleman families. So we're going to have different theories of Coleman families, which correspond to the different W's that you can use. So carrying graded coherent sheaves, which I call MWI for every W in WM, such that, well, okay, so let me just state this very quickly. So we call this map the weight map. So W inverse mu corresponds to so W inverse mu intersected with the support of MWI corresponds to systems of finite slope Hecke eigenvalues in this analytic cohomology. Okay, and so of course from that you get a kind of classicality theorem when you're in a classical weight, just from the classicality theorem for this space. So I won't even state that because I'm running low on time. But now the other result, the interesting, or the other result I want to state is what happens when you start with a classical cohomology class, which is not necessarily small slope. So if you have a classical cohomology class which is small slope, then of course it lands in sort of one of these spaces, and thus you know exactly where it lands on the eigenvariety. But so given a system of finite slope Hecke eigenvalues in one of these classical cohomologies, then we get, sorry, maybe let me even, yeah, so I'm kind of panicking due to lack of time here. So let me even call it HI. Then what do we get? We get a point of E in weight W inverse kappa for some kappa of length I, sorry, for some W of length I. And the last thing, which is probably the most important thing for applications, is that if this class comes from interior cohomology, so it's the image of the compactly supported cohomology to the normal cohomology, the image of the cuspal cohomology to the normal cohomology, then this point lies on a component of E of dimension equal to the dimension of weight space with dense classical points. Okay. So, all right, I'm way over time, so we can talk afterwards. Sorry for going over time, and I'm done.
Okay, thank you very much. Actually, you're not that much over time. It was a great talk. Yeah, thank you so much. And as usual, we are opening the floor for questions. You can kindly raise your hands. I'll try and spot you. If the co-organizers have questions, just, yes, Sarah, but, oh, you're on David, right? So hang on, I need to find you. David, is it just David without Loeffler?
No, I'm David Loeffler here.
But they're unmuted, so they can ask their question.
Unmuted. Okay, yes, please go ahead.
This isn't a question just so much as a remark. This theory of cohomology with these supports, I think some of this is developed essentially independently in the paper that Sarah and I recently wrote about p-adic regulators for GSP4. And we had an interpretation of it in terms of cohomology of the intersection of this U intersect Z with partial compact support along part of the boundary, but not the other part. And some of these functoriality properties and so on, just the basic properties of that cohomology, is also worked out in our paper. We got into a nasty technical point where we had something like your R gamma NM, and you can take a direct limit in M and an inverse limit in N, or perhaps the other way around.
Right.
And it actually matters which order you take the limits
Yes,
in.
certainly. And maybe the solution is you just don't want to do either.
Well, or
sometimes one doesn't have
depends what you're trying to do.
If you want to have a de Rham theory where you actually have, where you can differentiate stuff, where you have connections and so on, you really need to take some kind of limit. But of course, the finite slope part, it doesn't matter. It doesn't matter which order you take the limits in, because the limits are all stationary anyway, as you showed.
Mm-hmm.
Yeah.
Actually, I have a question, but maybe we can discuss it in more detail later. Namely, in the case of GSP4, I mean, Vincent drew this diagram with all the different regions and stuff. I mean, I'd be interested to know on which weights you can vary in which region and what constraints you have there.
So, right. So I think your question is maybe about the theories associated to parabolics rather than the Borel, because is it right? Like you want to not study the finite slope part for the Borel. So everything I talk about today was kind of the finite slope part for Borel. In fact, that's what we wrote about.
Yeah, sure. Right.
So in some sense, I can't really answer your question, but on the other hand, of course, we know what the answer to your question is.
Right. Okay. Yeah.
And I'm sure you do too. So, yeah. So I mean, in this story, we everything is varying in all directions because we're working with the full weight space and the finite slope part for the Borel. But there should be some other theories.
I was thinking, okay. I was thinking about other parabolics. That's true.
Yeah. But I mean, the recipe is incredibly easy to guess. So, and
well, I'll think about it, and I might send you an email about it at some point.
Yeah.
Thanks.
Thank you, David and Sarah. Other questions or remarks? Co-organizers would like to ask something. I can see you raising your hand. You could just start speaking. Oh, I see Tony Fang raised a hand. Let me unmute him. Yes, go ahead, Tony.
Yeah, so I guess I was in this argument with like the sort of shrinking closed and open sets. I mean, is that specific to the situation, or is there some underlying like general theorem that you're proving about equivariant localization for torus action?
Yeah, so I kind of wonder this. So I think like this kind of question has come up, and I think the problem is that like at least neither I or Vincent actually knows anything about these kind of theorems, and probably I mean, I think the point there is you're working with a group action. Here you're working with the action of a correspondence, but does it really matter? Not really. So I think, I mean, yeah, but I don't make any claim that this is some kind of particularly profound idea to compute the sort of part where the correspondence acts isomorphically in terms of something near all the fixed points. Like I think that many mathematicians would say that that's a completely natural thing to do. But I guess somehow in this business of coherent cohomology of Schnorr varieties, it kind of took a long time to get to this point of view, but okay. I mean, maybe you can tell me something about it, Tony.
I don't know the answer. I mean, I don't have any answer right now, but I just like, is there anything special about this stratification, for example, that?
Well, I mean, you need to be able to choose these support conditions so that you get these kind of containments of the U's and the right containments of the U's and the Z's. And from that point, everything is a completely general formal thing, right?
Okay. Yeah, I'm aware of some theorems, but I don't see that it literally applies in your situation. But it does seem like kind of a general property that you're using, or I don't know.
Yeah, I agree.
Any other questions, remarks? Okay, if not, I have a round of thank yous to do. So first for George, once more for his talk. The meeting will go on even after I finish my thank you rounds. So I'd like to thank all the speakers for actually producing in practice this wonderful workshop with so many great talks. And as the local organizers, I would also like to thank the organizing committee, Fred Diamond, Elena Mantovan, Yehuda Shalit, and Florian Herzig for all the work they invested in making it successful. And finally, for everyone that participated, thank you all very much.